Hey, this is Dr. B, and this is the Molecular Model Lab. In this lab, I'll begin with a lecture where I talk just in general terms about the elements hydrogen, oxygen, nitrogen, and carbon, how we can use models to put together molecules, how those molecules might have isomers that are present, how we can use creative methods to assemble these molecules using double bonds and or rings, and a little bit about how to draw these molecules both structurally and skeletally. Now, if I point the camera down here a little bit, you should see four elements. These white atoms are hydrogen. Red is oxygen, like the oxygen in our red blood. Blue is nitrogen. And black is carbon. And we'll be using these spacers as chemical bonds. Now, a couple of notes. I won't really use these very often. If we have a bond that just ends in space, I won't bother putting these little white tips on it. We'll assume that any bond that ends with nothing is simply has a hydrogen attached. Note that every single one of these has a tetrahedral shape. They all have four things that are attached to it. And their bond angle, can you see that it's greater than 90 degrees? It is a 109.5 degree bond angle. It is the best way or the most spaced way of putting four things around a sphere. That's a tetrahedron. It looks a little bit like a three-sided pyramid with a top. Okay, now the bonding characteristics of these I want to go over briefly. Hydrogen tends to form one bond. Oxygen tends to form two, so it would have a bond here. Here, I'll go ahead and assemble it. Here, as well as here. And when you do that, you end up with these two prongs. Well, those are the two lone pairs that oxygen has. Similarly, I won't assemble it, but nitrogen tends to form three bonds, and it has one lone pair. And when you put the three bonds on it, that space-occupying lone pair is right there. Similarly, these lone pairs of electrons do occupy space, and so this would be a water molecule, H2O, and it would have that bent structure there. So these very closely resemble reality in terms of their chemical structure. And finally, carbon, which we have right here, forms four bonds and has no lone pairs and typically has the 109.5 degree bond angle and tetrahedral shape. It's pretty easy to stick these things together. I've made two fragments in the interest of time, and if you just take two carbon atoms and stick them together, well, you got a molecule. And I did put all the little hydrogen atoms here. And so if you see this, you should recognize this as C2H6. This is known as ethane. A couple of things about it. At room temperature, it's free to rotate, so things like this are the exact same molecule thing. And once these things get longer, they're very snake-like, so that if you bend it around, it is the same molecule, whether it's straight or bent. Sometimes students show me S-shaped molecules. They think it's a little bit different, but in fact, it's the exact same molecule. So think of these as being very flexible, especially if they only contain single bonds. In this lab, one of the first activities you will be asked to perform is to create a molecule that has two carbons, six hydrogens, and an oxygen. I'll go ahead and show you how we might do that here. These two fragments are a good place to start. These are CH3s, and this is another CH3. So I do have the C2 and the H6 all ready to go. There, I hope you can see it now. Here they are. CH3, CH3. So that's C2H6. Why don't I stick an O in between? And that should work. I'll need one more bond. But once I stick that together, that should be C2H6O. I think we're good. It's a weird bond there. But there we go. And this is known as dimethyl ether. And in fact, I see my two carbons, my six hydrogens, and my oxygen. Remember, rotamers are part of the same molecule, so there's not really much we can do with this, but that's one way of putting it together. We can also put it together this way. Take a look at that and convince yourself that this dog-like molecule here is also C2H6O. 2 carbons, 2, 3, 5, 6 hydrogens, 1 oxygen. The relationship between these two substances is that they are isomers. One makes you drunk, one might be used as an anesthetic to make you unconscious. So they have different properties. Same chemical formula, different structures, those are isomers. And so that's 2 isomers of C2H6O. As the number of carbons gets longer, for example, in the next activity, you're asked to create C3H7N any way you want. 3 carbons, that's 3 blacks, 7 hydrogens, and 1 nitrogen. And there's a lot of different ways you can do it. Let's take a look at one of them. Here's C3H7N here. Convince yourself that there are 3 carbons. There is a nitrogen. And is it H? Oh, it looks like I'm missing a bond here. Can you see the error in this? Take a good look at this, and I do see an error. I wonder if you can find it. This, where is it? This carbon right here is missing a hydrogen. So let's go ahead and attach it. Now you might be saying, hey, look, there's a prong here. You're missing a hydrogen there as well. But no, that is nitrogen. It only forms 3 bonds. That's the lone pair of electrons. And like I was saying before, although it might not be the most stable conformation, this is the same molecule. If it's just like this, it's still that molecule. I always naturally try to show these as spread out as possible to prevent any kind of electron pair repulsion. So that's one way of doing it. Carbon, carbon, nitrogen, carbon. Oh, there's all sorts of other ways, right? How about carbon, 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 nitrogen? See that one? 3 carbons in a row, and then the nitrogen. We can also make it carbon, 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 and branch off the nitrogen. Notice that each of these two are linear molecules. It's all in a line. This is a branched molecule. So that's your parent chain, if you will, and then you have it branched at C2. But it is still C3H7N. And how about this? Very symmetrical molecule, trimethylamine. We can put each of the carbons on a separate spot there with nitrogen right in the center. We call these tertiary amines when they're tri-substituted, secondary amines when they're di-substituted, and primary amines. Here, I'll try to show it. Primary, because it's at the tip, NH2. Secondary, NH. Tertiary, just an N. Primary amines, secondary amines, tertiary amines. Fine. And I think there's even one more here. This is also a different way, all in a row with this primary amine at the end. So 4 isomers of C3H7N. Next, you are asked to assemble C2H6O2, 2 carbons, 6 hydrogens, and 2 oxygens. Let's go ahead and take a look at some ways we can do that. Let's start perhaps with this one right here. 2 blacks, 2 reds, and all 6 hydrogens are on the carbons here. We would call this a peroxide. This would be dimethyl peroxide. That's a lot of electron pairs right there, 4 of them right next to each other. Peroxides can be explosive and dangerous molecules. Perhaps it's not surprising. It's probably more stable spread out like that. This is a hydroperoxide, I believe, since it's got 2 oxygens in a row, but it ends with an H, right? C2, H3, 4, 2 hydrogens missing. I'm not going to stick them on, but there should be a bond there and a bond there, meaning we have hydrogens at those tips. Alternating your carbons can give you C2H6O2. This looks like an OH right here. We call that an alcohol. When oxygen is just spaced by carbon on either sides, that particular side there is called an ether. This looks like an animal a little bit, and I see an alcohol here. Can you see the OH? And down at the other tip, I see another one. This looks like ethylene glycol. This is a 1,2-diol, so two alcohols right there. This is known as antifreeze. This molecule it's very hard to freeze it and it's very hard to boil it. It's got a huge liquid range, so it's a nice candidate for keeping something cool without having it undergo a phase change. And that is C2H6O2. Two molecules you were asked to assemble were C3H8 and C3H6. Let me go ahead and grab those. Here we have C3H8, also known as propane. It's a linear molecule. Note that when you only have 3 carbons, you just can't branch it. This is the only way this molecule can be assembled. Propane, C3H8. You're also asked to assemble C3H6. Now, how are you going to do that? Well, nature does a lot of interesting things, including this. Double bonds and triple bonds can form. I love what happens when you do this. Can you see that the bond length got shorter if you compare this bond length here to that bond length there? I hope you can see that it got shorter. Double bonds are shorter than triple bonds. The bond angle changes to about 120 degrees, and that's reflected there. So just about all the things that happen when you do this cute little transformation are reflected in reality. It becomes more difficult to rotate. This thing cannot rotate, but this one can. That also is reflected in reality. So these models are just great for that. Now you might say, what if we put the double bond at this position here? If we called this 1, 2, and 3, instead of being in position 1 and 2, we put it at positions 2 and 3, which would be like this. Can you see that I put the double bond on the other side? But I hope you can convince yourself, and I'm missing a couple of bonds here. Here we go, this should be better. I'm hoping you can convince yourself that if you take a look, let me try to get these side by side. If you take a look at these, and I'll rotate them for you, they're simply the same molecule, right? If you can superimpose them on top of each other, you can prove to yourself they're the exact same thing. These are both called propene molecules because they have that double bond, that alkene. But it is not the only way you can assemble C3H6, and that's when you have to get truly creative. Check out this molecule right here. C3H6. Cyclopropane. These rings can and do form, and they can be very stable molecules. So there's cyclopropane right there. You might have noticed when you form a double bond to a ring, you lose 2 hydrogens. You go from C3H8 to C3H6. So this is called like a double bond equivalent, is when you form a ring. Finally, let's spend a few minutes talking about how to draw these molecules. Let me try to get this in focus here. Maybe if I draw something. Good. Let's draw C2H6O a few different ways. How about if we show it explicitly, every single bond? Remember, carbon tends to form 4 bonds. Oxygen 2. And hydrogen 1. So that's ethanol drawn using a structural formula. We could also type it out, and they call this condensed. This is handy when you're just typing it into your computer. But my favorite way to draw these things, because I'm lazy, is like this. And this usually, to show a functional group, they'll throw that H. But in this particular case, the hydrogens and the carbons are not shown. The carbons are the N's or the bens, which are here. I'm going to leave this like this. Let me redraw that and show you how we can translate this into a structural formula. Anywhere there's a bend, like here and here, there's a carbon, so we have two carbons. Not there. Sometimes students think there's one there, but draw that nice and close. That's just a connector there. So I'm going to go ahead and put a carbon there as I translate this into a structural formula. And hydrogens are implied. You know that yes, hydrogens are implied. Carbon should form 4 bonds. And can you see how there are 2 bonds here? We need 2 more. The hydrogens are implied. There must be 2. Here we only have this 1 bond, therefore we have 3 hydrogens that are not drawn but are there nonetheless. And that's how you can convert a skeletal formula here to a structural formula here. So that is structural, condensed, and skeletal. This was a skeletal structure. Let's do a quick quiz. I wonder if you can tell me what the chemical formula of this substance is here. I'm going to go ahead and put this on it. And I'm going to put this on it. There. So that's a nice structural formula. Let's count up the number of carbons. We've got a hexagon here. They call this a benzene ring. I think we have 8. If you put on these little dots, it can help you to not miscount. So we've got 6 here. This makes 7. This makes 8. This makes 9. Double check it. It looks pretty good. C9. Now let's find out hydrogens. As I go around the horn, think about how many hydrogens there are. These are double bonds here. So on this carbon, we do have 3 bonds. 1 must be missing. 1 must be missing. None are here. We've got all 4 bonds accounted for. None here. I can clean this up a little bit with my amazing erasable pen and get these a little closer so you know that's a double bond from there to there. None there. 1 here. 1 here. None there because we got all 4 accounted for. With this one we did draw. None there, none there. And what about this right there? We need 3 there. H, H, and H. I get a total of 1, 2, 3, 4, 5, 6, 7, 8. Let's count it again. Starting here, let's say 1, 2, 3, 4, 5, 6, 7, 8. H, 8, and O, 3. This is ortho-acetyl salicylic acid by night, known as aspirin. Okay, that's a little bit about how to draw these things.